Hi everyone, welcome to section 2.1. Our topic today is inductive reasoning and patterns. We just got done working on some in-class work looking for patterns. We also did the lab with the handshake. So now what we want to look at is just some kind of basic key ideas that we can build upon in this unit to help us learn how to use inductive reasoning and learn really what it is. So in the lab that we did, the first thing I asked you to do is look for a pattern. And that's really the first part of inductive reasoning. We're always looking for some type of pattern. See if it lets me type in here like I wanted. There we go. Look for, oops, I'll just go like that. So look for a pattern. All right, and then once you observe a pattern, we're going to make a conjecture. And a conjecture is really just an idea that we believe to be true. We're not positive yet if it is or not. We really can't prove it is, but we're just using our past observations to make some conjecture, some idea that we think is true. And then once we've created that conjecture, then the last thing you want to do is test your conjecture. And really, we did that with our handshake example earlier. All right, so just as an example, we're going to look at the first couple odd integers. And what we mean by the first n odd integers is like we're trying to come up with like an answer over here that uses the variable n. And the first thing we want to do is look for a pattern. So let's just go ahead and do that. Let's just start with, oops, I need to change that. Let's go red. And we don't need quite so thick of a line. I think that'll be good. All right, so we're just going to take one odd number. All right, and if we use one odd number, the first odd number is 1. And if I add up all the numbers in my list, I'm going to lock that in place. Forgive me. One moment. If I add up all of the numbers in my list, the sum of 1, oh boy, this is a tough one. Sum of 1 is 1. So I'm just going to put that here in my sum column. Okay, let's try the first two odd numbers. All right, so the first two odd numbers are 1 and then 3. If we add those values up, 1 plus 3 is 4. All right, and then we're just going to kind of repeat this pattern here until we can find some type of relationship between how many numbers we're using and what the sum is. So let's do 3 odd numbers. So basically that's going to be the 1, the 3, and the 5. Okay, if I add those all up, 1 plus 3 is 4, plus 5 is 9. Let's try maybe one more, well, maybe 2 more. We'll see if we can. Some of you might even start to notice a pattern here. Oh, sorry, my marker's being finicky. There we go. All right, so first 4 odd numbers. That would be 1, 3, 5, and 7. All right, so if we just add this here, 1 plus 3 is 4, plus 5 is 9, plus 7 is 16. All right, let's try the next one. So the first 5 numbers, that would be 1, 3, that's 2, 5, that's 3, 7, that's 4 numbers, and then 9, that's 5 numbers. If we add those digits all up, we get 25. Okay. What I want you to do before we make your conjecture, because right now we're going to look for a pattern, okay? To make your conjecture, I want you to look at this number, and then I want you to compare it to this number. All right, let's do that with each of these sets. The 2 compared to the 4. The 3 compared to the 9. 4 compared to the 16. So my question to you is, if I generalize this and say that this is n over here, what is the second column? Well, if you notice, basically each set of numbers got multiplied by itself. So if I have n odd integers and I add them up, the total is just n times itself. In other words, if there's 3, 3 times 3 is 9. 4 times 4 is 16. 5 odd numbers, 5 times 5 is 25. So if we want to write that a little bit cleaner, we could just say that's n squared. And that's the conjecture. So if you wanted to test it like we said we should, let's just try it with 7. So the first 7 digits, the first 7 odds would be 1 plus 3 plus 5 plus 7 plus 9. What is that? 1, 2, 3, 4, 5 numbers. All right, let's go another one. That's 6 numbers. Whoops. And then the 7th odd is 13. All right, so here we had 7 numbers. So n would be 7. If our conjecture is true, this should add up to be 7 squared. This should add up to 49. So let's just check that. Well, we already know, if we use our chart up here, we already know through here, this was already 25. That's what we got down below. That was 25. So 25 plus 11 is 36. 36 plus 13, yep, it's 49. So we just used inductive reasoning. We looked for a pattern. We made a conjecture. We tested it. And by God, we were right. All right, now, let's say we found, let's say we did this a whole bunch of times and we got to let's just check the first 137 numbers. And you were to list out all 137 of the first odd numbers. And you're like, oh my gosh, the pattern falls apart right here. This would be what is considered a counterexample. A counterexample basically shows that your conjecture is false. And for those of you that were in Angie's group when we did our small groups on Friday, we talked about the idea of like a tattoo. And so I'll pick on Angie again in my video here, but we just kind of used the example that Angie's been on a rough and tough path, and her dad said, we're going to get you to church. And so, they get to church and Angie rolls up her sleeve, or doesn't roll up her sleeve, but she whispers to her dad, said, Dad, you're not going to believe this, but I got a tattoo on my arm. And her dad in church was like, what? No way. Didn't really believe her. At this point, Angie's dad has to use inductive reasoning. She's kind of he's looking for a pattern in her behaviors. He's starting to make a conjecture. He's starting to say, you know what? I don't know if she's telling the truth or not. But his conjecture might be that Angie got a tattoo. Okay, that's his conjecture right now. He can't see it. She hasn't lifted her sleeve up yet to show her, or to show him. But for right now, he's thinking, gosh, Angie got a tattoo and I'm not real happy. Okay, if we wanted a counterexample of that, in other words, if we wanted to prove Angie was wrong, then the counterexample would be just pulling up the sleeve and seeing no tattoo. So that would prove that Angie wasn't telling the truth in that case. Sorry, Angie. Thanks for letting me pick on you. Okay. But counterexamples basically take this idea we think is true and it makes it false. Okay. Generally speaking, please put this kind of like in a box because this is a big idea. Well, actually, no, we'll hold off on that part. I'm going to wait till it applies to a more, like a different type of problem. So I guess the question we want to look at is, are all conjectures true? No, we just showed one that wasn't. You know, her dad just pulled up her sleeve and goes, oh, no tattoo. So this conjecture was not true. All right, let's try another one just to kind of use this type of logic, and hope you understand using conjectures better. Okay, so this conjecture says every even, I'm going to write, let me backtrack. I'm going to write the word conjecture above this example. And this is just an idea that somebody believed to be true. I don't know if it's right or wrong yet. You know, that's the thing with conjectures. You just kind of believe they're true until you prove them wrong. And that should sound a lot like science, where we make observations, you come up with your hypotheses, you accept it until somebody proves you wrong. And that's the way of the world. All right. This says every even integer greater than 2 can be written as a sum of prime numbers. So let's check it out. Let's see. It says verify through 20. I'm not going to go that far, but let's just start with the number 2. Can I break that down into something plus something where they're prime numbers? Well, sure. 1 is, oh, I'm sorry, great. I'm like, wait a minute. I'm already proving it wrong. Greater than 2. So I'm not going to start with 2. Let's start with 4. All right, 4 can be broken down into prime numbers. 2 is a prime number. So I could take 2 plus 2. That's a prime plus a prime, and it gives me a composite. Let's try the next even number. 6. Well, what prime numbers go into 6? Well, 3 doesn't necessarily have to go into, but has a sum of 6. So 3 and 3 have a sum of 6. That would be a prime and a prime. We're trying to come up with a scenario where there are not 2 prime numbers that can be added to get a composite number. So what about 8? Well, I know 3 goes in, not goes in, but 3 is a addend, I think is the proper word for that. 3 and 5 are both prime, and they add up to be 8. What about 10? Well, 3 and 7 work. Those are both prime. All right, and so you can go on and on and on and on with conjectures. That's why we say conjectures are things you can't prove to be true. You accept them to be true until at some point somebody finds a spot. Like, for instance, let's say somebody got to 24, and then at that point they were able to break the pattern down. I haven't tried it this far, but as soon as you can break the pattern down, you've proved a conjecture true or to be false. And I believe this one, for what I've tested, has been true. But again, it's just not something you can necessarily prove until you get to upper level mathematics, and then you get to some of your college math classes. And at that point, you'd be able to prove it. All right. So hope you learned a little bit about inductive reasoning, and you can start the assignment when you get done with your video. Thanks.